Good morning, everyone. Today, we will begin an important and powerful analytical technique used widely in chemistry, biochemistry, and material science: nuclear magnetic resonance spectroscopy, commonly known as NMR spectroscopy.
All right, let's jump right in. We're going to talk about one of the coolest tools in a chemist's toolkit: nuclear magnetic resonance, or NMR. Think of it as a way to create an incredibly detailed blueprint of a molecule, to see its hidden architecture. So, how on earth do you do that?
I mean, really think about that for a second. How do you see something that's literally a million times smaller than a grain of sand? You can't just, pop it under a microscope. We're talking about a scale that's just mind-bogglingly small. So how do you map it out? How do you figure out where all the atoms are?
Well, here's the trick. You don't see it. You listen to it. Seriously. NMR is a technique that basically listens to the unique song that the heart of an atom, its nucleus, sings. It's kind of like being able to tell every single bell in a giant cathedral apart just by its unique sound. Okay, so to get how this all works, we've got to dip our toes into a little bit of physics. It all starts with this wild quantum property that basically turns the nucleus of an atom into a teeny tiny compass.
This property is called nuclear spin. Now, not every nucleus has it, but the ones that do, like a simple proton, which is just a hydrogen nucleus, well, that spin makes them behave exactly like microscopic little magnets. They've each got their own little north and south pole.
So what happens when you take a bunch of these tiny magnets and stick them inside a massive magnetic field? Left to their own devices, they're all just pointing in random directions. But as soon as you turn on that strong external field, boom, they snap to attention. They either line up with the field, that's a comfy low energy state, or they line up against it, which takes more energy.
And this is where it gets really cool. We can hit these aligned nuclei with a quick pulse of radio waves. But it can't be just any radio wave. If the pulse is tuned to the perfect frequency, a nucleus in that comfy low-energy state will absorb the energy and flip up to the high-energy state. That perfect energetic match, that is resonance.
So we've got the basic physics down. Now let's see how scientists actually put this to work in a real experiment, inside a machine called an NMR spectrometer.
The whole process is incredibly precise. First, you put your sample right into the core of this huge superconducting magnet. That gets all the nuclear spins lined up. Then, zap! A short blast of radio waves flips some of them into that higher energy state. But the key is what happens right after. The pulse stops, and as those excited nuclei relax back down to their happy place, they spit that energy back out as a tiny signal. A super sensitive detector picks up that signal, and a computer turns it all into our result. So, we've gone from a chemical in a tube to a signal, which is now a graph. But this isn't just some random chart. It's actually a language, and if you know how to read it, it tells you pretty much everything about that molecule. And this is it, the NMR spectrum. At first glance, it just looks like a bunch of spikes on a line. But every single one of those peaks is a message from a specific group of atoms in the molecule, telling us exactly what its local neighborhood is like.
The first clue we get is something called the chemical shift. Think of it like a proton's address. Where that signal shows up on the spectrum, its position, tells us all about the cloud of electrons that's hanging out around it.
So why do different protons have different addresses? It's all about those electrons. If a proton is surrounded by a nice thick cloud of electrons, we say it's shielded. That electron coat kind of protects it from the full force of the big magnet. So it shows up over on the right side of the spectrum. But if that proton is next to an atom that's hogging all the electrons, it becomes deshielded. It feels the magnet much more strongly, and its signal gets shifted way over to the left.
Of course, to make any sense of this map, you need a starting point, right? A "you are here" sign. For NMR, we use a special compound called TMS. The protons in TMS are incredibly shielded, more than almost anything else. So we just agree to call it signal 0, and we measure everything else relative to that.
So decoding this whole thing really comes down to 3 key pieces of information. We've got the chemical shift, which tells us about the proton's neighborhood. Then there's integration. Basically, the area underneath each peak tells you how many protons that signal represents.
And finally, you have the splitting pattern. The shape of the peak itself tells you how many proton neighbors it has on the next door atoms.
And that's it. With those 3 clues, environment, how many, and who the neighbors are, we have everything we need to go from a simple graph of signals to the complete structure of a molecule. This is where the real power of NMR kicks in.
It's honestly just like solving a giant puzzle. You look at one signal and you go, okay, this has to be a group of 3 identical protons, and they're sitting next to a carbon that has 2 protons on it. Then you look at the next signal, and it gives you another piece of the puzzle. You keep putting these pieces together until there is only one possible structure that fits all the data.
And that's exactly why NMR is so critical. It is hands down the #1 tool a chemist has to figure out the exact structure of a new molecule. There's no guesswork. It's unambiguous. The spectrum tells you the answer.
I mean, it's just an incredible story when you think about it. We start with this tiny, weird quantum property, the spin of a nucleus, and we end up with the ability to design life-saving medicines, create new materials, and understand the chemistry of life itself. We literally learned how to read a language that was totally hidden from us.
It really makes you wonder, doesn't it? NMR taught us how to listen to the song of the atom. So what other invisible worlds are out there just waiting for us to map them out, if we can just figure out the right way to listen?